Time for a graph. There is a lot going on this slide, so let's take this one slow. What we're showing here are blackbody radiation curves for a blackbody at 3 different temperatures. And let me highlight that. See this red line right here? That's when the blackbody's temperature is 3000 Kelvin. Over here, that's when the blackbody is at 4000 Kelvin. And this blue curve here is at 5000 Kelvin. So let's see what else we have. Over here we have the wavelength in micrometers. So if you look at this point here, 1 micrometer, that's about 1,000 it's exactly 1,000 nanometers. So that's a little above the color red. So you're in the infrared spectrum here. As you move down, this little band here, let's see if I can just put a horizontal line on it. This is the visible light band. Okay, we start from red here, orange, yellow, blue, green, violet. What else can we show? Here's the intensity. This is how strong the light is. So the higher the curve, the more intense the light is at that particular wavelength. So another way of saying that, the x-axis plots the wavelength of the light emitted from the black body, and the y-axis shows how strong it is. We have one more line over here, this black line. This is a theoretical line. This is what classical theory, again, the theory before 20th century modern physics, shows what should happen to the blackbody radiation. More on that later. Let's break these curves down into a couple segments for better understanding. The red, green, and blue curves are actually measured data that was done in a lab. This black line is what classical theory said would happen to the color of the light at 5000 K. So notice, here's the measured data, 5000 K. Here's what the theory said it should be. Now, just look at the blue, the green, and the red curves here. As the object heats up, as it goes from 3000 to 4000 to 5000 K, what happens to the light emitted? That's right. Well, hopefully that's right. What we have is the light with the most intensity, which is kind of at the peaks of these curves. It shifts down the visible spectrum. So here, you were kind of in the infrared area. This was your most intense light right here, and you can see over here infrared. And then as you moved into this is the visible band. At 4000 K, you kind of had your peak at red light. At 5000, you were into the yellow. And you could imagine that as you increase the temperature further, the next curve at 6000 K might be a little further over, and you'd be getting closer to blue light. And actually, if you just look at this 5000 K, I was talking about where the peak is. Look at this. If you just take an intensity anywhere from here to here, all colors of light are visible. So you'll be seeing predominantly white light there. However, can you see a really big problem with the classical theory prediction? Again, that's over here, this curve at 5000 K, and here's the measured data at 5000 K. So, and of course, green and red were also measured. This is 3000 K, this is 4000 K, but this is the one that would correspond here. So I think I've already given the hint. What's wrong with the theory? The classical theory shows that the intensity of the emitted radiation, that's this curve here, you can see that it's coming off the chart here, and you can imagine it just keeps on going, and you don't have to imagine, that's actually what the theory says. So it's approaching infinity as the wavelength gets shorter, which is not at all what happens. You can see that the intensity of the higher frequency, the lower wavelength light, it does increase, and you can see it moving to the left, but it gets to a peak, and then instead of continuing on to infinity, it comes down. Okay, so shorter wavelengths means the light is moving into the ultraviolet end of the spectrum. Hence, a quite dramatic name was put on this. It was called the Ultraviolet Catastrophe.